Hello everyone. Thanks for selecting my talk from among so many good JSM presentations. My name is Marcin. I recently graduated from Texas A&M University, and this work would be impossible without the support of my supervisor, Dr. Matthias Katzfuss, so many thanks to him. Well, without any further ado, let us dive right into the main topic, and since, as they say, a picture is worth more than 1,000 words, we'll try to use, well, a bunch of pictures, animation really, to briefly explain what the problem we're trying to solve here. Okay, so this video, which you can see being played in a loop, shows the realization of a stochastic process proposed by Edward Lorenz in 2004, and in this case we use a grid of 960 points, which are distributed evenly along a circle. So Ed Lorenz postulated that this process has many properties that atmospheric variables might have when we measure them along a latitudinal band. So in this case, we're talking about the blue process, and each time we select 10% of the grid points, so 96 points, and we simulate data from a Poisson distribution where the intensity parameter is related to the value of the blue process. So the yellow circles represent the draws from the Poisson distribution, and the size of the circle corresponds to the value drawn. Maybe to make it more easier to conceptualize, we can think of the blue process as the lightning potential field, and then say the yellow dots are the observed lightnings or number of lightnings at each location, and then we would like to be able to infer the value of the potential field given the observations that we make about lightnings, and also we want to be able to do it fast, ideally in near linear time. Okay, so in order to see how we would go about this, let's first assume that we know nothing about the process, how it changes over time, and let's treat each time point separately. And for simplicity, we'll consider a case where our process of interest x is Gaussian, and we'll also assume that observations are Gaussian. We'll relax it later on. So the most straightforward thing to do would be to, we know the conditional distribution would be Gaussian, so we can use the expressions for the moment of the conditional distribution. And the only problem is that the covariance matrix of observations can be very large if we have a lot of data, and its inversion, as indicated by the red color here, that's the problematic element, will be very costly and even making the problem infeasible. So obviously this problem has been tackled in statistics before, and really a plethora of solutions have been proposed, but very few of them turn out to be suitable for filtering. So I'll propose one that and try to convince you why this one is suitable for filtering. So let's first select a few points. Let's say that the vector x is composed of elements, each of which correspond to one dot on the leftmost picture, either solid or empty dot. And let us group the points and use a different color for each group. So first we select a few points which we mark in black, then we split the rest of our domain, and then select red points on the left and green points on the right. And we can keep going like that, but here I'll show just one more level. We'll split the domain again with a vertical line, and then each quarter has then orange, yellow, and two shades of green. So in this way, we built a hierarchy of points with points of the same color belonging to the same level of the hierarchy. And let's see how we can use this hierarchy to build an approximation. So first, let's put all the elements of the vector in the order in which they were colored. So the black nodes labeled x will come first, and then the red nodes labeled x1, and so forth. Okay, so now comes the approximation part, and we will use a graphical model to illustrate it. So just a reminder, graphical model is a representation of the joint density such that if there is an edge from a parent to a child, then the joint density can be decomposed such that it will have a term with the conditional density of the child variable given the parent variable. But really what it encodes is independence relations. So in this case, for example, the red variables are independent of the green variables given the black variables. And this is really where the approximation comes in, because, well, in general, this might not be true. And maybe the key feature to describe this graph, though, is that all children are or all descendants are direct children of their ancestors. So what that means is, for example, if here we look at the orange node, we see that it is a child of the red node, which in turn is a child of a black node. So therefore, orange node is also a child of a black node because black node is its ancestor through the red node. Okay, so let's switch gears for now a little bit, and we'll talk about something else, and then we'll combine these two themes together. So another thing we want to talk about, and we're going to use in our approximation, is the incomplete Cholesky factorization. So I'm sure many of you are familiar with the regular Cholesky factorization. So here we modify it a little bit, and on top of the positive definite matrix A, which normally we use for decomposition, we also have this sparsity matrix S, which is lower triangular and has elements that are 0 or 1. So then we, as in normal factorization, we iterate over rows and columns, and then in the third line we decide whether we calculate a given element of the factorization or whether we set it to 0. So if we do, then we just use the regular formula for an ijth element in the factorization, and if not, well, we set it to 0. And then in line 7 we just calculate all the diagonal elements. So yeah, it's a slight modification of the Cholesky factorization. All right, so keeping this in mind, let's see how we can combine both of these concepts. So let's see what S matrix would correspond to the graph we had before, what it would look like. So in this case, S will have its ijth element equal to 0 if I and j element of the vector x are independent given the previous elements. So let us pick something in the first few columns, for example. So all first few columns of the S matrix are black, meaning they're 1, because black nodes that these columns correspond to are direct parents of all other points. But as we go further, more and more points are independent of each other given the preceding points, which are members of the ancestral groups. So finally, we notice that we can notice that the S matrix gets sparser and sparser as we move further away into the columns. And in fact, if we construct the approximation correctly, as the problem size grows, the matrix becomes sparser and sparser, which allows us to calculate the Cholesky factorization based on this matrix quickly. All right, so yeah, let's maybe stop here for a little bit and talk about the sparsity in more detail. So because it turns out that the sparsity of this S matrix is then preserved in several important matrices. So first, in the top right, we see that the incomplete Cholesky factor of the covariance matrix of our process that we talked about before has the same sparsity, and that's not really surprising because this incomplete Cholesky factor is right based on how we that's how we defined it. But then moving on to the bottom left, it turns out that the inverse of this incomplete Cholesky factor also has the same sparsity, and we can actually prove that it holds. So the key upshot of this is really fast computation, because we already know that L can be calculated quickly because there's only so many non-zero elements. But in the case of its inverse, we know there is only so many elements to calculate, and we know exactly which these elements are. So the inversion is also fast. And maybe another property worth mentioning, which we can also prove, is that while L is an incomplete Cholesky factor of sigma, it is actually an exact Cholesky factor of the covariance matrix of X, given that our conditional independence assumptions are actually satisfied, so actually hold. And then finally, even though it might be less apparent and requires some technical assumptions, the matrix L tilde, which is a reverse Cholesky factor of the precision matrix lambda, also has the same sparsity, and we'll talk about it in more detail on the next slide. Okay, so with all these pieces in mind, let's go through some matrix algebra and see how all these elements help us solve the original problem. So let us recall that what we started with looked as follows. We wanted to compute the moments of the posterior distribution of X given Y, and the key difficulty lied in inverting lambda, which we said could be a very large matrix. And it turns out that after we perform the incomplete Cholesky factorization and denote the factor as L, we can approximate the inverse lambda as the inner product of L inverse plus the product of H and R matrices, which are generally sparse. And using what we know about L and its inverse, we can conclude that our main bottleneck, lambda inverse, can also be rapidly calculated. Okay, now we proceed to a less obvious part, and for brevity, there will be a lot of detail that will remain hidden. So let us first recall that we defined L tilde to be a reverse Cholesky factor of lambda. But what is it? What is this reverse Cholesky factor? Well, so we'll define P to be a order reversing permutation matrix, and then L tilde can be defined as we see on the left side of the curly bracket. So once we have L tilde, we can work through the matrix algebra and see that the outer product of L's is approximately the posterior covariance, and that using L tildes, we can also calculate the posterior mean here. So, and as we said, since L tilde is sparse itself, deriving this matrix also shouldn't take too long. Okay, so let's bring all these pieces together and see how we can use them to approximate posterior inference using all this. So let's start with what we're given: data y and sparsity pattern encoded in S, then the moments of the prior distribution and H and R matrices which relate y to x. Okay, so what we want is the approximate posterior distribution, here represented by a sparse factor of the covariance matrix and an approximate mean. Okay, so first we obtain the incomplete Cholesky factor of the prior covariance, and in line 2 we calculate its inverse. Then in the third line we compute the approximate matrix lambda, and in line 4 we calculate its reverse Cholesky factor. So this allows us to quickly compute the approximate mean in line 5. And as a side note, let me just mention that even though we discussed only the Gaussian case here, this method can be easily extended to non-Gaussian data, and the way to do it was developed by my colleague Daniel Zilber and Dr. Katzfuss, and they show in their paper how to do it for any exponential family. Okay, so now that we know how to do inference at a single time point, let's see how we can incorporate our knowledge about the temporal dynamics. So let's say that using the domain knowledge we can define the function script E, and since we want everything to be Gaussian, we assume that whatever the model does not capture is normal with some known matrix Q. And then using this framework, we're interested in the filtering distribution of xt, that is, the distribution of xt conditional on all the observations up to this time point. And for completion, let's just observe that if we started with a Gaussian distribution, then all the filtering distributions will be Gaussian as well. Okay, so the standard way to address this problem is the extended Kalman filter, which is based on the idea of recursion. So let's assume that before we get to time t, we already know the filtering distribution at time t-1. So, well, let's see how we can use it. We'll proceed in 2 steps. So first, using the knowledge about how the process changes, we will make the best guess about its current state. So that's how we come up with the forecast mean. So then we linearize the temporal evolution operator around this mean and use it to propagate the uncertainty captured by the covariance matrix. It is obviously an approximation, but for models without too much, quote unquote, too much non-linearity, it works fine, as in the case that we started with. And on the other hand, if the evolution matrix is linear, well, then it is just then there'll be no approximation here, and we can carry out exact posterior inference. And okay, so then using our best guess of as a prior distribution, we can then carry out posterior inference. And okay, so let's see in more in all gory detail how this would all fit together. So okay, so the final step of our method, so-called extended Kalman-Vecchia filter, proceeds as follows. So again, we start with sparsity matrix S and the moments of the distribution at time 0. Then for each time point, we have a vector of observations, a transition function, so to speak, and then matrix that captures model errors and H&R matrices, which again relate the latent state with the observations in the Gaussian case. Okay, so the algorithm produces approximate mean and a factor of the covariance matrix. Okay, we start by decomposing the initial covariance and obtaining the initial factor, a sparse factor L00, and then at each time point we linearize the evolution operator and then calculate the forecast mean and the forecast factor LTT simply by multiplying the latter by E. And then next we calculate the elements of the forecast covariance that will be used in posterior inference, and only those elements, which makes it quick. And as a final step, we use the hierarchical Vecchia approximation described before to obtain the representation of the filtering distribution. Okay, so that's how it works, and let's take a quick look at how we can evaluate this method. So these 8 plots show their filtering results using 3 different methods evaluated using functions of mean squared error and log score. So we simulated data from several exponential family distributions whose parameters were determined by the value of the latent Gaussian process, which was simulated from the Lorentz model. And the lower is better for each case. So the more accurate method would have a lower score. And the red line corresponds to the filter based on our hierarchical vector approximation, and the blue dotted line corresponds to filter based on the low rank approximation of the process. So we see that our method performs better in all cases here. All right, well, this is it. Thank you everyone for tuning in, and I encourage you to check out our paper, which has all the details and proofs and much more than I was able to cover in this presentation. And again, thanks for your attention.